Hello, am I audible? Hello, hello, am I audible?
Yes, sir.
Is the screen visible?
Yes, sir.
Yes, sir.
Fine. So yesterday we had seen to this part practically Carnot cycle is at least 99% possible with the assumption or the condition under the condition that it is getting executed inside the dome where you can execute at least the isothermal processes infinitely slow. And if you could execute the isentropic processes with a wet mixture, then you can execute the Carnot cycle. As I said, may not be 100%, but at least 99%. We will go for the analysis. The refrigeration effect is H1 minus H4. This is H1 minus H4. This is what my heat absorbs. So refrigeration effect, heat rejected is H2 minus H3, which is equivalent to HFG at that particular pressure, temperature TH, whatever corresponding pressure also. Then the compressor work is H2 minus H1, and the expander work using turbine or any kind of device that would be H3 minus H4. So net work is the compressor work minus the expander work, or similarly the heat rejected and heat absorbed. The difference between them is one and the same. If you change the sign suitably, you will get the same expression. Okay. So the COP would be the refrigeration effect, that is the heat absorbed, divided by the total work. So at such H1 minus H4, it remains as it is, but H2 minus H3, if you divide it by this H1 minus H4, then this is my HFG. H1 and H4 as per your requirement about the pressure and corresponding temperature, since they would be same as the phase change taking place. So in other words, this particular formula shows that COP is a strong function of this HFG, H1 and H4. So once your HFG is fixed, in other words, it is the function of HFG only, because the moment you lock this HFG, you have to just draw the vertical lines. So you cannot change H1 and H4. Wherever this point correspondingly, there would be 0.4. Wherever this 0.2, there would be corresponding 0.1. So I would say that H1 and H4 are not independent. They are dependent on this HFG. So as such, one can say that COP is a very strong function of this HFG. And as such, whatever temperature and corresponding pressure you fix for this particular level, HFG is basically H2 and H3 related. So accordingly, automatically you have to lock H1 and H4. So as such, the governing factor is HFG. Okay. Any doubt in this? Any doubt to anyone?
No, sir.
Okay. Now we know that practically such a cycle, except inside the dome, is not possible, because it's impossible to construct this or use the same motor, employ the same motor for infinitesimally slow speed and infinitely fast.
Sir,
execute the
in the
isothermal.
previous cycle, how do we know where to stop and start the different process? Like, although we can.
That's what I said. Na? You have to lock the HFG. The moment you lock 2 and 3, 1 and 4 automatically get
Yes, sir, but I mean, it is easier to draw on the graph paper, but physically, when we are operating the cycle, how do we know that we have to stop at this particular mass fraction or temperature pressure? Maybe not that.
If you lock the process on the graph, then you know the X1 part, that is the dryness fraction. So you have to design a compressor to deal with such wet steam, and the compression ratio also you know, H2 and H1. So you know the compression ratio. Same is for applicable for the expansion, because the ratio remains same. You start from the liquid expansion. That is what is the practical difficulty. You have to stop, or rather If it follows the given expansion ratio, then it will end up with the given dryness fraction x4.
And sir, a wet and I mean the mixture present at x1 is has both vapor as well as
Yes,
steam, right?
yes.
So compression will be not physically very difficult, right?
Physically possible, but it is very difficult for the analysis purpose, because theoretically we can do anything we want, but practically a compressor which is dealing with the inlet condition as the wet itself, that is what is difficult, because to compress the ideal gas, you can deal with it very easily, but a wet mixture and to compress, then practically there are difficulty like sealing and lubrication, all such practical things come into picture.
Okay,
So
okay,
to
okay.
execute the isentropic compression, practically that is what is the problem. That's why I said you can achieve up to 99% of the Carnot cycle, may not be 100% always possible. Because executing isentropic process for the ideal gas is very easy. Put the super insulation and blah blah blah. But for the wet mixture, it is very difficult. Since
Okay, sir.
continuously the dryness fraction is changing, right from x1, whatever is the value, let's say 0.6, up to x2. For x2, dryness fraction is 1. So during the compression process, the dryness fraction is continuously changing. Now, who will be responsible for the change in dryness fraction? Naturally, the heat transfer. And you are not allowing it. You want the process to get executed as the adiabatic one. Correct? S1 equal to S2. Then there is a problem. So that means you have to deal with the internal energy changes. If no heat transfer is allowed, enthalpy is changed. That means basically the internal energy change. Because PV work we have seen is very small. So the internal energy changes are to be controlled as expected, as desired. And for the wet mixture, that is very difficult task. For the ideal gases, it is okay.
Yes, sir. Understood.
And same as the logic for the expansion, reverse side. How do I expect a reversible expansion, I have to say isentropic expansion, with a wet part? They always remember this thing that your expansion starts as a liquid part. Liquid expansion is very difficult. It's an incompressible one. At the beginning, it is entirely liquid, 100% liquid. We are assuming that after the expansion, let's say it reaches over here, then maybe dryness fraction some 5% and 10%, whatever it is, and then finally let's say over here 40%. Then it is okay. But what at the start? There will be tremendous inertia for the expansion because it is liquid. Gases expansion is very easy. Liquid expansion is very difficult. So even if it follows certain expansion process, what is the guarantee that it will be the isentropic one? That is the practical difficulty. So I said you can achieve up to 99%. Better the control over the process, higher would be the resemblance to car. 100% is impossible. But at least I can think of doing something in a way to execute as close as possible to Carnot. The main point to be emphasized is not about the irreversibilities, but when you execute or try to execute the same process for the gases, then it is highly impossible practically because you have only one motor. In the piston cylinder arena, you are using gas, the piston cylinder arena. So half of the cycle you wanted to move with a infinitesimally slow speed, and half of the remaining cycle that is infinitely fast. Two reversible adiabatic means two isentropic and two isotropic. That is impossible. Here you get rid of that one part, half of the cycle. You need only one motor to be, what I can say, run for only the compression expansion process. For the heat rejection, heat absorption, there is no requirement because it's basically dealing the phase change. So at least I get rid of that practical limitation. Let's call it restriction. So that is how you can think of making something practical, may not be 100%, but at least better than the gaseous one. 100% gas, even though it is ideal gas, but practical difficulty is how you are going to execute the compression expansion process and the heat rejection, heat absorption process simultaneously. That is the problem. Here, at least you get rid of one process. One means two process out of the four. Isothermal heat rejection, isothermal heat absorption, you get rid of. You need not worry about the speed because there is phase change, latent heat. When you use the gas, everything becomes like a sensible heat. Sensible heat rejection, sensible heat absorption. So there is a problem. Are you getting it?
Yes, sir.
Now we discussed about all these practical limitations. So that is why the cycle slightly modified. And we call this as a Brayton cycle, you know. That is the for the engine, that is power generation, steam power plant. So, or Rankine cycle, whatever similarities. So same Brayton cycle, which is used for the gas turbine power. Gas turbine is done, na?
Yes, sir.
IC engines. So we reverse it. And the name given to it is Bell-Coleman cycle. Okay, so as shown in the figure, refrigerator section, which is the space to be maintained at a lower temperature at the bottom, then that compressor, then the heat exchanger, where you can see about the cooling water for the heat rejection part. Then the air becomes cold, it comes to the expander part, then further cold. So I have written as very cold air, and which will go to the refrigerator to absorb the heat from that chamber or the section. So logically here I'm using air, which is not changing the phase. So it's such a very, very sensible heat part. So compressor, heat exchanger in bracket heat rejection, then the expander and the refrigerator in bracket heat absorption. Logic same, only the medium is changed. No phase change is involved over here. So work gained from the expander can be used to drive the compressor. Because expander is like free to rotate, it's a turbine, so small amount of energy it would generate. So why to give the entire power to the compressor from the external part? Let us use it to come होने जाता जाता. So the compressor work can be reduced. And we know that compressor work is the input denominator, COP. Refrigeration effect divided by compressor work. So if I could reduce the compressor work, my COP will be increased. Anyways, turbine or whatever expander you are using, that work otherwise would be just like a wastage. So if I couple the thing together, that is why I have shown in the schematic figure over here as the single shaft. So whatever power generated by the expander can be directly coupled with the compressor. The external work to be done on the air compression part would be reduced. Fraction of it would be directly achieved from the expander. So if I could reduce the denominator, my COP will be high. Clear? Any doubt?
No, sir.
So this is my PV diagram and this is my TS diagram. So one can observe, let's say for example, TS diagram, in the Carnot cycle, there were the isothermal processes, which were difficult. Two isentropic, we have kept C. And instead of the isothermal processes, now we have converted into the isobaric process. Why isobaric? Because here only the heat is getting rejected. Why pressure change would do that? Or let's say over here in the refrigerator also. It is heat absorbed. It is air, not changing the phase. So MCP delta T. Why pressure would change? So here heat rejection and here heat absorption. There the isobaric pressure remaining constant. It's only the temperature getting changed because it is a sensible heat part. So if it is a sensible heat rejection, temperature would be reduced. In the refrigerator, there is a sensible heat addition, the temperature increases. The pressure remaining constant. So we change the isothermal processes of the Carnot cycle with the isobaric processes. And same is applicable over here. The PV diagram, PV chart also 1, then compression. So naturally volume reduces, pressure increases. Correct? So this is 2. And state 2 to 3, pressure is constant. It is only that the temperature is getting reduced. Obviously, pressure constant, temperature reduced means volume reduced. So that is why 2 to 3. Correct? Even V1 upon T1 is equal to P2 V2 upon T2 if T1 and P2 are same. Or let's use the same logic, same notation. P2 V2 upon T2 is P3 V3 upon T3. Or P2 is equal to P3. So naturally, as the volume reduces, temperature reduces. Sensible heat rejection. Same is the logic over here. Clear with the diagram?
Yes, sir.
So heat absorbed in the refrigerator. So that is my process 4 to 1 over here. So it is MCP delta, T1 minus T4. Right? Heat rejected in the heat exchanger over here. Condenser, we call it. Now here we are not using the word condenser and the evaporator. Why? Because there is no phase change. So how I can say condenser? It's a sensible heat. So I'm not calling this as the evaporator. I'm not calling this as the condenser. I'm just saying simple refrigerator heat exchanger. Okay, fine. So heat rejected. So it would be this process 2 to 3. H2 minus H3. Okay. Now if I change the process, let's say you are not able to execute the adiabatic process, and if I have to execute a polytropic process, compelled, then instead of gamma, it would be n upon n minus 1. Correct? So P2 V2 minus P1 V1, whatever is the n value, naturally greater than 1. P2 V2 minus P1 V1, that is my compressor work. And same is the logic for the expansion. So P3 V3 minus P4 V4. Do you agree?
Yes, sir.
Fine. Now we know the interrelation for Cp, gamma, Cv, R. It was a second year thermodynamics. Correct? So now I can substitute. So n upon n minus 1 and P2 V2 minus P1 V1. This is compression. P3 V3 minus P4 V1. Expansion. And negative है इसके लिए साइन होता है. Now I can say PV is equal to MRT. Nothing wrong in that. So MR anyway is taken out in the constant one. Here I get T2 minus T1 minus T3 and plus T4. Correct. Now if I want to shift this R in terms of gamma and Cp by using gamma and Cp, then I know the expression n upon m minus 1 and here gamma minus 1 over gamma. M as it is. And instead of this R, I'm using gamma minus 1 over gamma into Cp. And I try to rearrange this term. So this is plus 4 minus 3 plus 2 minus 1. Alternate sign, decreasing order. So plus 4 minus 3 plus 2 minus 1. The moment you execute the adiabatic process, n becomes gamma. So this gamma cancel, gamma minus 1 cancel. And what you get is only this part. So if you are not able to execute the adiabatic process, this bracket or rather product will come into picture. If you execute successful to execute the adiabatic process, then this bracket getting cancel. Gamma minus 1 is gamma बन जाएगा. N and gamma cancel. So what I get is this only. Fine. Any doubt?
Yes, sir.
So this is what is the formula for COP. What is the refrigeration effect? This related to T1 minus T4. So this is enthalpy change. So MCP into T1 minus T4. MCP उड़ गया. What remains with you is only the terms of temperatures. So this is another classical way to resemble this to Carnot cycle. COP of a Carnot cycle can be expressed in terms of temperatures alone. Here also the same thing. And the moment you execute even the isentropic process, even this bracket also is cancelled. There are purely temperature terms. So this is how it resembles very, very closely to the Carnot cycle's UV. Do you agree? Nothing I have to worry about. Any other factor?
Yes, sir.
Okay, N and gamma are also polytropic index or adiabatic index, whatever you call that. So as such, it is a unitless part. And temperatures also finally getting cancelled. So I can say even though there would be some N, that means this bracket and this bracket will be some kind of multiplication factor to the temperature factor, not changing the units. So let's say some K constant. So T1 minus T4 divided by some constant type this times this particular bracket. Ultimately one and the same logic is that it is the ratio of the temperatures alone and as such resembles to the COP of the Carnot cycle. Any doubt to anyone?
No, sir.
1 minute break for calculators. Yeah, फटाफट calculators लेके आ जाओ. Okay, ready?
Yes, sir.
Let us read the example first and try to collect the data. Well, polymer refrigerator operates, मतलब air.
आंसर आएगा हेमंत?
कैलसी लौटा ना तू पहले.
Is the calculation correct or not? Hello, am I audible?
Yes, sir. Yes, sir, but you're not presenting.
Is the screen visible now?
Yes, sir.
Fine. Is this calculation correct? Are you getting 482 or not?
Yes, sir. Approximately.
Fine. Then similarly find T4. Is this correct?
Yes, sir.
Okay, done. So now you know all the values. Heat extracted from the cold chamber. That is what is asked. And basically refrigeration effect. So it is Cp into T1 minus T4. Heat rejected Cp into T2 minus T3. Upper part, heat exchanger. Now the network done. So here you have to take care for this N and gamma part. N upon N minus 1 into gamma minus 1 over gamma. So this is my network. Refrigeration effect already calculated. Network just now calculated. So that is what is COP. Ultimately, you are doing the same thing. This is Cp into T1 minus T4. In the denominator, you are substituting this. So Cp getting cancelled. M is assumed to be 1, so no problem. Finally, you get the same expression. Is the calculation correct?
Yes, sir.
Okay. So COP 1.27, 1.3, whatever it is. An air refrigeration open system operating between 1 megapascal and 100 kilopascal. So T1, T2, no. Okay. Keys, pay the attention to the unit. One is megapascal, other is kilopascal. Is required to produce the cooling effect of 2000 kJ per minute. And is loudly given cooling effect. That means refrigeration effect. And 2000 kJ per minute. You can use it as it is. You can use it as kilowatt, convert it whatever way you are comfortable with. Temperature of the air leaving the cold chamber is minus 5 degrees Celsius. So that means T1. Cold chamber means refrigeration chamber and leaving. So that is entering to the compressor at such T1 and leaving the cooler is 30 degrees Celsius. Cooler means heat rejection. Hello.
Yes, sir. You are stop presenting, sir.
Internet connection. Most useless thing. Most unreliable one. That is why mechanical is best. Is the screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Calculate. T4 and T2. Calculate. The calculation is correct. Pressures you have to take care. One is 1 MPa, the other is 100 kPa. Units are different. Change it. Is T4 correct?
Yes, sir.
Okay. So the moment I come to know T4, I can calculate the refrigeration effect. T1 minus T4. M is 1, let's say per kg, and Cp. Okay, so refrigeration effect done. Is the value correct?
Sir, from where did 302 came from?
Eh?
302 Kelvin.
302, 30 degree. It should be 303.
Okay, sir.
Here.
Yes, sir, I saw that.
Is it a typing mistake or the calculational mistake? 156.9 comes from 3. Using 303 or 302?
So 303.
So that is a typing mistake from us. Otherwise, a calculational mistake. Fine. So you calculate the refrigeration effect. Is the value correct?
Yes, sir.
Triple 1.66. Okay. Now, you don't know the mass flow rate. You have to calculate it because you want the power in kilowatt. European power in kilowatt. So I need to calculate the mass flow rate. It is a refrigerant. Air is the refrigerant. So you have to calculate the mass flow rate. So refrigeration effect is known. Refrigeration effect per kg. This is total refrigeration effect. And this is refrigeration effect per unit mass. What is the mass flow rate? This is the answer.
Yes, sir. It's correct.
So calculate it. Is the calculation correct? What happened? No, it is presenting now. Am I audible?
Yes, sir.
Is the screen visible?
Yes, sir.
Yes, sir. Both values.
Okay, so T2 is also calculated. Then the compressor work. So instead of Cp, I'm using gamma upon gamma minus 1 into R. Otherwise, you use Cp. Why it would change? Someone use just Cp and calculate the answer. M you have calculated. Instead of gamma times gamma upon gamma minus 1 times R, use Cp. 1.005 or 1.003, whatever it is. And T2 and T1 just now calculated. Are you getting the same answer?
Yes, sir.
Yes. So now the compressor work is done. So refrigeration effect numerator, compressor work denominator. Sorry, expansion missing. So find out the expansion work. T3, T4 just now we have calculated. So use the same M into Cp into T3 minus T4. You should get the same answer.
Yes, sir.
Okay. So in the denominator, compressor minus expander. So what is the net work? Cycle work, compression minus expansion. Always you will come to know, you will see that compressor work is much higher. Here you can see expansion like almost like just less than double. Compressor work is just less than double of the expansion work. Because expansion is free, compression you have to do it. So this is the network, and that is your denominator. So you get the COP. Is the COP calculation correct?
Yes, sir, it is correct.
Fine. And the power required. So the total cycle work per unit time. Here it is given in per minute converted to second. So that will give you kilowatt. Calculation correct?
Yes, sir.
So always
sir.
as a thumb rule, after going through a couple of numericals, here the COP is 1.076. Here COP is 1.27. So always remember as a general thumb rule, as far as all the refrigeration systems are concerned, the air refrigeration cycle COP slightly greater than 1, between let's say 1 to 1.5, not more than that. Okay. When we study vapor compression system, COP would fall in the range of 4 to 6 or even 7 also, because it is anyways theoretical. And when we study vapor absorption refrigeration system, then the COP will fall down even lesser than 1, maybe 0.7, 0.8, 0.9, something like that. This is a general thumb rule. If during your calculations in MST, AC, whatever, if your COP comes out to be something different, then that is a direct hint you have to cross-check the calculations again. I repeat the values for air refrigeration slightly greater than 1, let's say 1 to 1.5. For vapor compression cycle 4 to 7, or let's say 3.5 to 7. And for vapor absorption, it is a fraction lesser than 1. Always keep these values in your mind as a cross check. If your answer goes wrong, means COP values, that means your calculations, there is some mistake. You can cross check. Fine. Okay. So here I stop with the first part, and the second part I have to start with. So let me load that first. Oh, sorry. Now this is a PDF file, because a PPT file got corrupted. Are you able enough to see the screen?
Yes, sir.
Yes, sir.
So whatever we have studied is the basic air refrigeration cycle. Now the application, that is aircraft refrigeration.
Q
Now
I.
you- Eh? What happened?
No, sir, by mistake.
Someone said something and which I was not able to hear properly. Is there any doubt?
No, sir. No, sir. You may continue.
Now whatever we have analyzed as the numericals are just like the glimpses of how to apply the basic theory. I can twist the numerical the way I want, because you have done with the IC engine course, means gas turbine basically. You know the Brayton cycle, then you know the compressor also, correct? Thermodynamics, and even in a maybe gas turbine also. So you know the effect of clearance volume and the volumetric efficiency. Then what else for the compressor part? Mm, Polytropic compression process, and then irreversibilities and all such kind of things I can put in a single numerical. So I will say compressor efficiency, let's say 90%, or volumetric efficiency 94%. So accordingly, your final enthalpy values would change. You can calculate MCP delta T as the theoretical one. And then you have to consider the turbine efficiency, compressor के लिए volumetric efficiency, turbine के लिए adiabatic efficiency, means basic polytropic one, and something like that. Okay, so this is just how to apply the basic theory. Now, under the assumption, and a valid assumption, of course, that you have successfully completed your SY Tech Mechanical and TY Tech Mechanical. So I can twist the numerical by implementing all those previous year theory courses. So you have to be ready for, or you have to be ready with that knowledge also. Compressor volumetric efficiency, then mechanical efficiency, adiabatic versus polytropic compression process, expansion process, turbine efficiency, blah, blah, blah. Okay, any doubt to anyone? I'm making it clear at this moment only.
No, sir, no doubts.
Don't ask me the question, ये कहाँ से आया? Compressor volumetric efficiency. If I said similar question in MST, because you know it. Okay, so let us start with this part now. Aircraft refrigeration system. So when we fly in an aircraft, naturally we are at the higher altitude, so temperature is already reduced. Right? At the higher altitude, temperature is anyways lower. Then why do we need the refrigeration? So the answer is given below. There are many components which contribute towards the generation or liberation of the heat, basically, and because of which ultimately the temperature inside the cabin, passenger cabin, would be increased, and it increases considerably. What are those components? The first part is the heat release from the occupants. Whenever there are human beings, naturally the metabolic activity is going on over there, plus the excitement energy. So naturally, a tremendous amount of heat getting released as a biological part from the occupants, that is the passengers. So that is because of which the second part is a physical part, ramming of the air. Now, what is that? I will tell you with the help of a figure. Maybe aero people knowing it. Yes or no? Aero VJTI.
Yes, sir.
Yeah. So stagnation enthalpy. I hope you are aware.
Yes, sir. Yes, sir.
Good. Then solar radiations. You cannot get rid of the sun. So naturally radiations are always there. Then the control devices. There are hundreds of control devices in the cockpit and even in the passenger section also, of course. So because of that, again, naturally small amount of energy multiplied by number of such devices or equipment. So that also contributes considerably. And the air resistance. Whenever there is a flow, the resistance. So frictional drag part, because of which there will be further increase in the temperature. And heat is free to flow from here to there. So even though something happens at the exterior part, it can be very easily transported to the interior part. Exterior part means body, airplane body. Interior part means cabin. Okay, so all these factors basically contribute towards the increase in the temperature. So heat release from the occupants for a normal healthy human being, the average value is 300 kilojoule per hour per person. Now you can calculate. Let's say you are traveling non-stop journey Mumbai to किधर जाने का? New York. चलो, let's see. 16 hours journey. So 300 kg per hour into 16 hours. And let's say you are flying in 747 or 777. So let's say there are 450 passengers. What is the amount of heat? 16 into 450.
7200.
Right? It's a visible one. Am I audible? Is the screen visible?
Yes,
Yes,
now
sir.
it is.
Fine. So calculate 300 into 16-hour journey into 450 people. How much is the energy? Or rather heat?
So 2160 megajoules.
So now you can see yourself that it is like a power plant. Correct? And the second part from the occupant side is the sweating. Sweating due to nervousness. Sweating is a phase change phenomenon. So naturally again latent heat transfer. 300 kJ per hour is a sensible heat transfer. There is latent heat transfer also. Either a person who is traveling for the first time, excited energy, and even fear also little bit. So few people go into the higher energy level state is equal to h mu, and remaining people would be nervous, fear. So because of that, the metabolic activities also increase drastically. Palpitation, blood pressure increases because of both reasons, excitement also and fear also. So that also generates the heat. Otherwise, either kahan se? Why the blood pressure increases? So there is tremendous amount of heat getting generated from the people. Then the second effect is the ramming of the air, which I can summarize in a simple way as the dissipation of the fast moving air relative to the airplane. So now you recollect your fluid mechanics course, I think SEM 4, where you might have dealt with the one-dimensional compressible flow. Am I right? Or it is in SEM 5?
SEM 4, yes.
4 only, no? Huh. So there you come to know about the stagnation enthalpy. So when you suppress the velocity, enthalpy increases. When enthalpy increases, temperature has to increase. Do you agree? I hope you recollect
Yes.
that graph. So naturally, when the temperature increases, then the heat, in terms of what, basically increase in the heat. Correct? So ultimately, there is an increase in the incoming air temperature, which is not a desired factor. So I need to control that. I need to dissipate that heat. Are you able enough to imagine it and digest it or not?
Yes, sir.
I'm taking it granted because it is done in SEM 4, as you said. Not very specific to aero. Aero people may be knowing it in much depth. But even general student also is aware because you have completed your SEM 4. ये ऑप्शन कोड आला था चैप्टर आई डोंट नो
Yes, sir.
Are you-
Centrifugal compressor में पढ़ा है sir.
हाँ so one dimensional compressible flow or whatever is that topic, but I hope you are aware with the stagnation enthalpy concept h naught, which is let's say h plus v square by 2g basically. Able to recollect or not? Other than aero people. Aero people are on the advantageous side, but that doesn't mean that other people are not aware. I hope they are aware. Yes or no? Any other non-aero people? Are you getting it or not? Am I audible?
Yes, sir.
Yes, sir.
So any other non-aero people? Are you able to get it or not? VJTI racing people. Are you getting it? Ramming effect. What happened? Hello, am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
Nobody is answering. What is the problem? Are you
I
getting
think
it or
they
not?
haven't heard.
So yes or no? If yes, I will move ahead. If no, I have to repeat. That is my job. That is my responsibility.
No, sir. No, sir.
Any non-hero people, anybody from VJTI racing or SRA.
Sir, I'm non-aero, sir.
So are you getting what is the ramming effect? When you try to kill the velocity part, velocity component in the enthalpy, the total part is the enthalpy plus the velocity, kinetic energy. If you kill the kinetic energy and make it as a stagnation part, then naturally enthalpy has to increase. Why? Because the total enthalpy has to same. Enthalpy is what energy? Total energy has to be same. Who said? First law of thermodynamics. So if I'm converting one form to the other, kinetic energy to the enthalpy part, then if kinetic energy is to be reduced, suppressed, naturally enthalpy has to increase so that the total will be same according to first law. And if
Yes.
enthalpy is increased, that means the temperature increases.
Okay, sir. Okay, sir. Yes, sir. Understood, sir.
Fine. Okay. So third part, solar radiation. As we already discussed, you cannot get rid of the sun. So whenever there are radiations through the glass planes also, which is like somewhat reflective part, and the aeroplane body, which is a metallic part, so more absorption, and that is why we put it as the glaze part. Absorptivity is equal to reflectivity. Kirchhoff's law. Same 3, no, sorry, same 5, heat transfer. So we try to reduce the radiations, but we cannot get rid of them completely. Do you agree?
Yes, sir. Yes, sir.
Good. Then heat release due to the control devices. There are hundreds of devices. How many of you have seen the cockpit of any big aeroplane? Not in YouTube video or any photo. In reality, physically. Has anyone seen the cockpit? How many devices are there? Aero people. Huh? Have you seen the cockpit?
सर हम लोग छोटा
No,
प्लेन
sir.
बनाते हैं सर अभी.
Right.
Sir, we make RC planes, sir, not.
तो क्या हुआ?
Sir, उसमें cockpit इतना सब कुछ important रहता नहीं sir, interior मतलब. Mostly
I
about
know,
exterior.
Papa. I have taken 2014 batch to US.
Yes,
We
sir,
have
sir, I
seen
know,
the
sir.
cockpit at London Airport, Heathrow Airport. We have seen. We have requested. What you call Hawaii Sundari, air hostess. We requested. She shown us the cockpit. It's like a huge room. Hundreds or rather thousands of electrical or electronic gadgets are there. That's why I'm asking. Has anyone seen during your childhood traveling days or whatever? Has anyone traveled internationally since
No,
your
sir. We
child?
have not seen the cop.
Has anyone traveled international travel, not domestic? International travel means maybe Airbus 300 or Boeing 777 or something like that. I just want to know how many can realize the big size and shape of the commercial aeroplane. That's why I'm asking. Has anyone traveled? 450 people in
Yes, sir.
the
Yes,
cabin.
sir.
So which airplane did you travel?
Sir,
Airbus or Boeing?
both, sir. 777 and A380 as well.
Good. So now you are able enough to imagine the huge size of the entire plane, let's call it,
Hmm.
including the cabin, then the cargo, and then the cockpit.
Yeah.
So actually, if I want to control something for the life safety of 450 people simultaneously, excluding the crew, just talking about the passengers, and that too in a suspended section position, no ground touch, then naturally the factor of safety would be much, much higher for all these control devices. So there are thousands of control devices and they liberate tremendous amount of energy. So on an average 10 to 15 kilowatt, medium size plane agar koi bhi le lo, Airbus or Boeing are like quite a large one, but even you consider a medium size plane, then 10 to 15 kilowatt. That is like per second. And let's say again you are traveling for 16 hours direct journey, Mumbai to New York. Tremendous amount of energy getting liberated. So at such, the cabin temperature can reach up to that of Nagpur. Okay, it's not so simple to imagine. And that is why there is a requirement of the air conditioning for the passenger section. So if you understand, if you analyze the total heat generated inside the cabin and which is responsible to raise the temperature up to 40, even 50 degrees Celsius, then naturally we need the air conditioning. So that is why aircraft refrigeration is important. Agree? Any doubt?
Yes, sir.
This is somewhat I can show for a schematic part. So solar radiation everywhere, universal. Heat released by the occupant, so that is inside the cabin. From outside radiation, then ramming effect, then air resistance, which is the frictional part. And the control device is also from the inside. So 2 inside factors, 3 outside factors. Okay. As a result, tremendous amount of heat generated. We need to take care of that. So there are different systems which there in your syllabus we need to analyze. The very first is the basic aircraft. How much time left here?
2 minutes.
5 minutes.
And then there is no sense in explaining this. It would take time. So let us stop over here. Tomorrow we have a lecture, right? Thursday. Thursday lecture.
Yes, sir.
Thursday lecture I will complete this part, so that will complete our 2 chapters and then immediately the vapor compression cycle, heart of your syllabus. Fine. Any doubt up to this part to anyone?
No, sir.
Okay, good. So I should end the meet.
Yes, sir.
Yes, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you.